Okay. Okay. Mm, okay. So I'll start with week 10. Okay. Start with week 10, which is 1 minute.
RNNs.
Yeah, but till okay. Okay. So I'll cover RNN, LSTM, and GRU. Okay. Uh, Okay, fine. So, so what happens in RNN is this: we have uh, so we have these words, right, which we are going to, let's say, convert it to one hot vector. Okay. Uh, for example, let's say there's like this, like something like this. So if let's say some word has so let's say this three words are there in my vocabulary. So something called vocabulary you will come across several times, which are all the words or all the tokens, right? So I mean, token never used in course, but token means you can take in any way, like let's say word, sentence, or even character by character. Okay, depends on how you want to use it, but we'll generally use words in this course. Okay, so number of this thing. So let's say this is the one, and let's say you want to represent cat, you will represent like this. Mat, you represent like this. So rat, you represent like this, right? So these are a word embeddings, you can say, right? So these things now you can call them as embedding, and these are like basic embedding, nothing much about. But if you use let's say some problems, let's say I have context, and I want to, based on context, I want to predict the word, or I have a word, I want to predict the context. So this two kind of problem, then you will get better embeddings, like you will get really vectorial representation of them. So you need embeddings before you go to RNN. So in RNN, when we feed embeddings of it, right? So uh, those are also numbers in some form. Okay, so whatever dimension you can decide, let's say 4 dimension, 5 dimension, that kind of single. I mean, it is going to be vector only. Okay, embeddings are going to be vectors only. So this you will require, which will going to feed in the RNN. Okay. So okay. So now what is RNN? So let me first write the equation of the RNN. So first, what we do is we try to find the current state of it, which is, we use sigmoid for that. We use input. So this input is going to be this vector. Okay, some vector will give it, and we take previous output. I'll just write for now. I'll explain. Okay, and then we predict from this. So maybe let's say y hat, and t also, like at each timestamp we are going to predict. So we'll use some kind of uh, activation, but most likely it is softmax only. So that, and we use v here, and we use current terms. This will go here, and we'll use c as a constant, right? So this is just the equation. So to explain you, let's say I have this is my uh, RNN layer. Okay, just a layer of it, and here my input will go. Let's say if it was let's say cat, right? Then I didn't need it for, like, maybe I would have done with this. Okay, so this is my inputs going inside, like this. Okay, it will be inputs going inside. So this is my input thing. So how many okay, let's say I have uh, sorry, this is if this is input layer, then this is my hidden layer. So this is input layer. So input layer, or just input you can consider, right? So this will be based on how much dimension embedding you have used, right? So here it was 3, then 3 will be there. So you don't need to actually draw neurons. Let's say neurons are here. Okay, this is a hidden layer, and then something you'll get output also, right? Um, yeah, you'll get something like using softmax. Okay, so this is based on software. This is sigmas. I mean, I'll write sigma, let's say, and this is softmax. Okay, so say S, I'll write, and this is input. So uh, what- okay. Um, okay. Yeah. So I was going to give input here, and what will happen is, let's say I wanted to predict how many how many weights are there, right? So this is my input, and x, this is my x, and this is my layer, hidden layer, and I want to predict first what is this u, right? U is this one according to our formula that is going with xt. So you know that the three here, let's say four are there, right? Let's say four uh, neurons are there. Then you can definitely say that, let's say three inputs were given, then like all of them will go to first weight, and then similarly all of them. Then you'll go, you know that the dimension of this are going to be, let's say uh, how many uh, how many rows? Three rows and four columns, right? This is what dimension is going to be. If we write, let's say W in our when we learned back propagation, all like that time, like 1 1 1 1 1 2 1 1 3. Yeah. So sorry, three, no, 4 cross 3. Okay, four are there, and each will have three inputs. So this is going to be 4 cross 3. Okay, so you can say maybe, input dimension is, let's say, n, or v. You can consider maybe v, whichever you prefer. Okay, and this is going to be the dimension of the so this is the dimension, this is dimension of v, this is dimension of the hidden layer. Okay, so v, d cross v. Okay, now what happens in rnn is, first we have this input, we got some output, right? This output we got. Now we are going to feed each of the output to itself, right? To all the neurons. Okay, like this, all the neurons, and similarly it will, second one will also do, it will feed to itself. It will send to others also, right? So if you do this, then how much you will get? 4 cross 4, right? 4 cross 4 matrix you will get for all these weights, right? And you can call maybe d cross d. So that many parameters will be here. If you don't get it this way, let's say at t equal to 1, we sent x to this 4 neurons. So a little bit here, 4 neurons we send it. And we got something as output, right? Now at time step 2, what will happen is, let's say this is my similar, this 4 neurons only hidden layer, because we don't change hidden layer in it, right? But now I'll have another input. So this is my input, this was my input here, which went here. This is my another input. Okay, you can call this x2, this was x1, and now it will go definitely. So this will have this will again have like 4 cross 3, let's say 12 weights, right? But here what will happen is, the first uh, it will come from here, let's say here, then here, then here, then here. So it looks like this, the one I drew here. This one is going back to itself, right? That's what it means, that it's going back to itself. I mean, if it's not time wise, then you can maybe think uh, as it is going inside, right? And then one is going to the next one, then third is going to the third one, and fourth one. Like likewise, all four of them will do it. Okay, so this is how it looks like. Which color? Okay, let's say this will draw, and so on. Okay, so this is how RNN looks. So this is we call U and W, and so what will be B then? B so whenever we do addition, right, we need similar dimensions, otherwise addition won't happen, right? So from this we can say that, I mean, we have four neurons in this, so we'll require four biases, right? So that also can be, say that the B will be how much? D cross 1, right? D cross 1. So this is B. So we covered that U will be how many columns? D columns, and no, sorry, D cross N. This is going to be D cross D. This is going to be D cross 1. Okay, D cross N. So this is how dimensions of each of them. Now let's go to Y. So Y is output, right? So now it will generate some output. Like we'll say this will generate some output, uh, and so on. So it will go in softmax thing, right? And it could be uh, so. Um, so what happens is we decide softmax based on the output, right? So let's say in Hindi word is, let's say mm, I mean, let's say ja, or something, right? In English it is go. Now maybe this is one character, right? One character or something. It could be one or bigger or something, right? It requires more, let's say one hot, more one hot, and or less one hot, depends, right? So depends on that, you decide how many neurons you require in the softmax layer. So that if you decide, then that many parameters you will require, V parameters you will require to connect them. So it will get connected through, let's say, this V parameters, right? So in V matrix, Y is VST plus C. So V is going to be, so we know what is ST, right? So this is going to come out as D cross 1. Okay. If you can see here, so this will each will give 1, right, which is D, and we'll apply sigmoid over that, so it will not change any dimension, right? So we'll have D cross 1 ST, and we wanted to multiply something with it, right? So we need, at least we need D columns, and something we'll use here as output. Maybe I'm not sure which sir use, maybe M we can use for now, and that will give how many? D cross 1 only, right? So just so you sorry, we'll apply softmax over it also. Okay. Yes. So Y and ST.
So this plus will be D cross 1 or M cross 1? The C.
Yes.
Plus is C.
It
Um,
has to be
M
M
cross
+1.
1. Sorry, M cross 1. Okay, this should be M cross 1. Okay. Then we'll apply. Yeah. So then we'll apply softmax over it. So something we'll apply softmax, and we'll have M cross 1 only, right? So we'll have M outputs, and that is going to be Y. So we'll get Y that way. So this is what RNN is, forward propagation. We did forward propagation. If we want to do backward propagation, so okay, any doubt in forward propagation? We can.
No, sir.
Okay. So let's do back propagation little bit. So I'll not go too much into this, because it's kind of difficult to figure it out, because so we'll use loss as cross entropy, even cross entropy calculated at each time step, right? So we add all of the cross entropy. So we'll have ln, let's say, y t c. So t is means true character at that time step, right? So we'll have some time step, maybe okay, minus ln, or if I represent it as, let's say, minus lt theta, I'll sum all of them from t equal to 1 to whatever time step we go, right? So that and lt theta is minus ln ytc. Okay, so t since which was true character at that point. So let's say our predicted probabilities of let's say four are there in the output. So should be in the output. Let's say the probability came out to be 0.2, 0.3, 0.1, 0.4, something. So this is softmax thing. So after softmax, you got this. Maybe this was correct, or the correct one was this. Then you'll use this one, right? So minus ln 0.4 you should have used for this time step at maybe t equal to 1. Then in t equal to 2, something like this again you will get, and you should know what is true of that. You will again compute that. Let's say it came out to be 0. Let's say ln 0.2, and so on. You go ahead and then you add all of them. Okay, so if you add all of them, you'll get this total cross entropy. You can maybe call total cross entropy. So this thing you'll get. So this is loss of this. Now okay, now we have the loss. We wanted to do back propagation. So one which is easy is dl by v, right? Because we know dl by y hat, or y hat tc in our case doesn't matter. So we know y hat at times m, and we know y is dependent on let's say something which is inside, right? Whatever is inside softmax, or this let's say y is v output of v st plus c, then this whole term I'm calling as a. Okay, by a, then I know dow a by v, right? So this is what I have to do, and I'll be able to get to the uh, back propagation, right? So at each time step I have to do it. So this is for l uh, yeah, this is what total loss, right? Now so there is no like um, what do you all there is no recurrent here, right? There is no recurrent here. So at each time step you'll get individual this loss, or this derivative. So you don't need to go back into time. Let's say when we started, let's say we are now in time to step 2. Then for this step you'll get this. You don't need to go time step 1 for this. uh, for u and w you have to go back and time step. We'll see that. Okay, so this thing, and we know this part, that this is y hat minus y, and this thing also we know that whatever is with the v, in this case it was st, maybe transpose of that. Okay, so this is what is a basic multiplication which we did in back propagation. Okay, so this is what you will get. Now let's say if you want to do with w, right? So before I do, let's say um let's say s3. Okay, I'll start with s3 only. U u time x3 plus w time s2 plus b, and sigmoid of that. S2 is sigmoid of ux2 plus ws1 plus b. S0, sorry, s1 is sigmoid of ux1 plus ws0 plus b, right? So this is what all three of them are there. Now if I wanted to figure out what is dow s3 by dow w, then what will happen is I have s3 which depends on u x3 w, or should I give, so I have s3 depends on u w x3, or let's say x3 w s2 and then b, right? I want to figure out with B, with W. Okay, so that I can do. I have this, but there is one more thing, that I have something here also, right? Because S2 is now again have U, X2, W, S1, B. So this is where we have again W. So this is possible. Now again in S1 we have U, X1, W, S0, and B. And S0 is, you can kind of consider as constant. So we don't need to do that, because that is something we give it initially, right? So yeah. So here, sorry, not this. In S1 also we have this W, right? So again I have to go. I will take this and plow it here, right? So this there is this three kind of thing I have, and I have to add them, right? They kind of going in different direction, you can consider or something. Yeah. So if I wanted to do, let's say, T by W, I would have done dow S2. Sorry, dow. Um. Yeah. So I have to do with L theta. So first I would have done is I would have done with y hat with whatever you call A. Then A has this ST. So yeah. So now A by maybe S3. Okay. I'm actually L3. So currently I'm talking about T equal to 3. So this is going for 3. Then S3 has this called W. So this is what I have now. And then what happens is this remains constant, right? So this will always be there. Now this one plus, because there are two branches of this, right? I should have dow S3 by dow S2, and then dow S2 by W, right? This part should I have, and then again I should have something like this, right? Uh, so it will all add up, and you'll have this thing, right? Which big thing, which you can maybe write dow L by maybe S3. Then there is something like summation of T equal to 1 to T dow S T divided by dow S T, not this T minus 1. And what is left? Dow, I think it will be S1 by W. Okay, so something like this you'll get. And whatever the formula is, so basically this huge thing will be there. You have to go across each path and then compute the back propagation.
Excuse me, sir.
Because, yes,
So the third term is not part of that summation, right? Dow S1 by dow W, it is out of that summation.
uh, it is out of the summation.
I mean, either way,
Maybe
can you
not.
just
Maybe
put
not. I think
parenthesis?
it is like ST. Sorry. So this is going to be ST minus 1 by W. It's not out of summation. They both are. So this two terms we are getting, right? This two, then several more terms. So this how you'll get. I don't think so. It will be out of this. Um.
Okay.
No, if it is like this, then it will cancel out, no?
How?
This dow is t minus 1. Again, you have dow is t minus 1. Something to be
But
different, or it will
The
cancel?
chain rule, no, Samit? How will you cancel out?
No,
You
the
actually
chain
don't.
rule is okay. But in summation term, if you write like this, then I don't understand.
yeah, okay. No, it will not cancel out. You can maybe check. So this is the formula.
Then
I'll just write.
representation has to be something else.
No, it's summation only. So So this terms are there, right? I didn't wrote later on, but this terms will be there. It will be more one. It will not cancel out. This means you have to take with respect to this and W, right? Like I did. See what I did is I took dow S3 by dow S2 first, and then dow S2 with respect to dow W, right? For this time step. Then inside this dow S2 by dow W, I'll again write more, like dow S2 by dow W is going to be we are here. So okay, I mean I don't need to dow S1 by dow S2 by dow S1, and then dow S1 by dow W. This multiplication will be there. Okay.
Is there any place where I can get any question on this which I can practice on?
I mean you can't. I'm not sure, because generally we don't ask this kind of numericals. It's not possible for you to solve this in exam period of time.
I was
So
just thinking about that only. All right, sir.
yeah, but
Thank you.
you can make up the questions. So you know what you do. You have to draw these things. I can only solve by this. Otherwise, it's not possible to visualize this. So if you have this, maybe you can try it. Okay.
All right.
Yeah.
Thank
So
you.
I was
When
going
we're
to write.
programming this, I think it's just that del s by del s minus 1, we have to kind of keep it as a like we have to keep overriding, we have to keep carrying that a variable back when we're running that reverse loop for programming. We have to just keep carrying that delta s by delta s minus 1. From there, it becomes easy to calculate the gradients for u and w. I think it's not.
Yeah.
It's kind of intimidating seeing it on paper and convoluted, but like when it's the programming is not that much difficult also.
Yeah, sure. Yes. Something plus like this will appear, which I'm not sure why. I mean, seriously, I'm not sure why this plus is there, because whenever I do different derivative, it doesn't require it. I mean, there is something called implicit, explicit, and all. I get it.
Yeah.
But that's okay. So dimensional, right? So this should be d cross d, like because if w is going to be d cross d, then derivative of that should also be d cross d. Otherwise, what you will subtract out of it later on, right? When you'll do the subtraction of the gradient, some learning rate and all. So this should be that. So how will you get that? First, you'll do let's say 1 cross d, and this is going to be d cross d, and this is going to be d cross d cross d. So ultimately, like, this is going to be tensor, this is a matrix, and this is a vector. All of them will give you a matrix. So you'll get a matrix at the last. Okay. This is going to be tensor. Yes. So this is back propagation of RNN, and yeah, I think that. Yeah. Okay. So that's what is RNN. Now we'll go and see what is LSTM. So for LSTM, let me use image. That would be much better.
Sir, the vocabulary size doesn't have anything to do with the number of parameters in RNN, right?
No, it has, right? I mean, it depends on the embedding size. So vocabulary has impacted embedding size, and embedding size will impact the parameters.
There's a previous year question with 10 embedding size, 8 hidden size, and in the end they've given vocabulary size as 12. So that's the. Anyone else solved that
So that
question?
is so vocabulary size. What is that? I'll tell you. So let's say this is something you'll send. Okay. That is embedding. Embeddings you will send. Correct. Inside RNN, just consider this RNN. But what you will get is some output, right? Y hat. So this should be of vocabulary size, right? Whatever vocabulary is, that's what they it means in the question. I get that question, but that's what it means by vocabulary, that whatever output requires a vocabulary, use that. So maybe you can consider that embedding size as input and vocabulary size as output. Okay, that's what it means.
I
That
get it,
here
yeah.
this many output, this much size of output I want.
Yeah, you can just have the matrix. You can just design it like that to get that output.
Yeah, correct. So that's what, because this will give softmax we use, right? So output will get something of in that way, like some 0.42, 0.32. Then we have to use that one hot only to verify which word is that, and which word was predicted, right? Let's say this, if this is what it is, like, then this might have higher probability or something, right? Later on, when we'll do prediction, this is training period. That's why I have this. When in training, when testing period, I don't have true prediction. I'll have this. Then I'll say, okay, this word, whatever word that is in this position, should be the prediction, right? So you can say this is maybe vocabulary, and this is
Got it, sir.
another type of input. Okay, so yeah, I was. What? Yes, can- this is much better.
Copy image is there at the very bottom of that option,
Sorry.
context menu. You can copy that directly. It's at the very bottom of that context menu. The last option, I think it's copy.
Yeah. Okay. This one.
Yeah, here in the bottom. Yeah, copy image. Yeah, you can copy that.
Okay. So this is what our architecture of LSTM looks. I know sir never used it. He used it something different. But this is how it looks like LSTM. Okay. So uh, so for now we first let me say what is it. I'll just represent what it is. So this all is are sigmoids in our case. Okay, all of them are sigmoids for our case. And cross means multiplication, addition, and this cross, and here also multiplication. Okay, we use instead of CT, previous cell state, we use ST. Okay, so we use ST in course, and this is of course HT only. Previous, this should be all -1. This is XT. Okay, fine. So this is what architecture is. Again, you will get here ST, you'll get HT here. So you'll get two outputs. You are feeding three inputs. Okay. Now, this long chain which is going here is called long-term memory. This small thing here or something like this, you can call this as, or you can call ST as a long-term memory, HT as a short-term memory. Okay, short term, or LSTM. So that's why the name is long short-term memory, LSTM. Okay, that's why this name comes up. Now, okay, let me tell you what this part is. So this part is forget get. This part you can call as input get, and this part, the last part, is output get. Okay. So okay. So what happens is, let's say you get, let's say you get a vector of 4, 5, 2, 3, something, right? So this is, let's say you can maybe think that this is ST-1, right? This is what it is. You wanted to forget something, right? Or you wanted to remember it totally. So one thing what you can do is you can multiply this by 1. So if you multiply this by 1, that means you want to remember all the things. You don't want to forget anything, right? Or another thing you can do is you can maybe multiply it with, let's say, 0.2. Then what you'll have is or 0.5, let's say 1 by 2. Then what you'll have is 2, 2.5, 1 and 1.5, right? So this is what forget get does. It helps in like wiping some of the memory. If you don't want at all, you can maybe do 0 as well. So if you use 0, then all the things will be wiped out. So how does that decide? Decides on this sigmoid. So this first sigmoid is there, which will decide that how much you should forget, how much should yeah, that's all. How much you should forget, that is being decided by this first sigmoid, right? So if we look into the equation of it, so this sigmoid is there. It doesn't need to be one only. Okay, it can have a layer of sigmoid as well. So this is just a representation of it. It can have multiple neurons in it, but the layer is of sigmoid. Okay, uh, then what we do is we give st minus 1, ht minus 1, and then let's say xt, right? This three thing we give. Let me write here only xt. Wait, this three things we give. Now based on this, you have to figure out again the parameters, right? So it depends on the number of neurons and what not, right? So we use we use mm, okay. The equation we use is okay. So sigmoid of I mean okay, ft. Ft is so if you see this uh okay, not all of them are going to sigmoid. Sorry, my mistake. This two only going to sigmoid. That that was mistake. Only ht minus 1 and xt. This two will go. Okay, this is short term memory, and this is my input or at current types, right? This is going to be in, maybe you can have one hot encoder or embeddings, any kind of embeddings. This you will get by, for now, like at 0 time trip, you will initialize something, but later on you will get using this calculation, right? So we'll come up there how you will get that is. So sigmoid of what you'll use one weight for the ht minus 1 plus we'll use u as we used previously in RN also, uf you can call for xt, and we'll use bf. So this is how you will get sigmoid. So now you can figure it out, right? How many parameters you will require. So this is a sigmoid, and how many neurons are there? Based on then you can decide, right? Let's say 3 is the size of xt or something. Then so 3 is the size of xt 100 or something, and 4 neurons are there. Then you will require 12 of them, right? Each of them going to each of this. So 3 and so on 4. So the dimension of this is going to be, you can maybe is there any constant used? Mm, okay. Let's say d d what is d is the number of neurons maybe you will take. Oh, I was can't talk about this way. Do so UF. So dimension of UF is what is it? D and N, right? So or T cross N. D rows of this is D, and this is coming inside as N. So D rows and like this. So this will be dimension of UF. WF is dependent on HT minus 1. So that we have actually what we do is how does it do it? It concatenates the both of them. So we have HT minus 1, which is concatenate with the XT, right? Like this. So you'll have single vector, and then it goes to this sigmoid thing, right? But the weights of this are being called different here, so that's why we are doing it. So this might be, let's say the dimension of XT was 3 cross 1. This dimension could be 5 cross 1, like anything. Then that many vectors you will require on in this, right? Yeah. So it could be anything, right? So 5 cross 3 or something. So that many you will require of WF. Then BF will be something which how many neurons are 3? 3 cross 1, right? 3 cross 1 in this case. So D 3 or sorry, I use 4 there. So D whatever D cross 1 will be the dimension of B. Okay. So this 3 are there, U, W, F. We can have dimension like this. We can figure out the dimension this way. So it depends on what is given to you as an input. So and what is coming out as ST, right? So see ST or HT dimension should be given to you, and X dimension should be given to you. Based on that, you can decide how many parameters you will require for get, right? One more thing, that whatever HT comes out, ST will also have same dimension. So that you know, it will do addition here. See, we have to do addition here somewhere here, right? Multiplication. This is element wise multiplication. So you can maybe in our course we use this dot Adam product. Here will do element wise multiplication. Here will do element wise addition. Here will do element wise multiplication, and again here will do element wise multiplication. Okay, so just in case, so we if you want to do element wise multiplication, right, then ST and HT should have similar dimensions, otherwise it will not work. So both of them will have similar. So if ST is given to you, that means consider that ST, let's say ST or HT, any of them is given to you, ST or HT, then consider that is going to be the dimension of output. Okay, and XT is the input dimension which will be given to you. So something on that basis you can figure out how much is dimension going to be of U and W and B of this case. Then we'll do multiplication later on, right? So yeah, so this we figured out. We have to multiply with ST. What did I do? Something. So it's there. So yeah, we have to do element wise multiplication with ST minus 1. Now we are here. Okay, we are here. We did this part. Sigmoid we did. Just sigmoid. That's all. Nothing else. Just sigmoid thing you have to do, and you are here. So now we'll do ST minus 1. Is it okay? So we'll have ST minus 1, and the output of the get, which is FT. Okay. Multiply with FT. Yeah, element wise, just in case, like, so this is like element wise multiplication, and that's all. Like, that's all we have to do. We are here now, so we can reach here now. Now we have to do input, right? So we forget something. This was the vector maybe I got. If I do element wise multiplication or something, so you know that element wise multiplication means I'll do multiplication of, let's say, if it's there, then h or ft will come up. Let's say this is was st minus 1. This is ft. Then this is going to be of 0.2, 0.8, maybe 2, 4. It could be anything. Depends on the sigmoid value, right? So this is how you'll get, and you'll do element wise multiplication, and you'll get this. So now we need input something, and then we'll add that. So whatever input we get from this short-term memory, we're going to add that, and uh, and you get the point, right? That we'll use again sigmoid. Then I get it again. See here also same thing. So here but both of them are going there. So ht minus 1 and xt, both of them will go here. Sigmoid will apply it, and you'll get some output. Here again we are doing something same, like ht minus 1 and xt. We are sending it here, and we are finding sigmoid. So we are doing two kind of sigmoids, and then we are multiplying them. Okay, element wise multiplying them, and then I am adding it to here. So that is called input get. So whatever I get input output I'll get from this two thing for getting and inputting. I'll bring it here. Now what I'll do is I'll again use similar thing, ht minus 1 and xt I'll go here. Now let's say I'm here. So from this I'll get again a vector, right? A vector I'll get a vector here. I'll apply sigmoid over that. So I'll get another vector here. I'll do element wise multiplication, and that's what will generate two things, xt, and this st is already defined. It will be based on this addition, right? So this is what a structure of LSTM. If you don't get it any part of this sigmoid, I can explain, but you get the idea, right? That this is what we are going to do in the LSTM. That similar inputs are going again and again in the sigmoid thing. So that's why you will have one equation for input gate, one for get gate, one for this output gate, and then there is some another equations also, right? Which are addition, multiplication, or so. This is what it is. I'll write all the equation together, and that's all. That's what LSTM does. So you forget something, you write something here, and then you give the output based on that. Okay, fine. So this image is important. Yeah, go ahead.
So one question in the exam, if something like this comes, are we expected to remember the entire sequence, or would you give the image and we can just deduce from the image?
You don't need to remember the sequence because let's say if equations are given to you, let's say you can figure it out, right?
Yes.
If you wanted to solve the question, so you don't need to do that.
Okay, if equations are given in the same way.
You had mentioned last time that you will tell us whether you had said you will clarify to us whether we can expect numericals from week 10.
Yes, it's going to be there, numericals. Yeah, Rn. Let's say forward propagation of Rn and such kind of equations is there, right? Parameters, calculations. Let's say what are the parameters of this? Now input is given. st is given. So this 3 is given to you. You can figure out the parameters of anything, right? All will have equal dimension of parameters. So that's why similar name UW, but they are different. They are not same parameter. That is the case. So yes.
So in this context, just while I try to solve some previous year question, I just for the parameter calculation I got stuck because the answer is not matching. Will you take up that problem and just show us to calculate the parameter? I can share the problem.
Yeah, sure.
Just hold on, sir. I am sharing my screen.
Oh, you are sharing the screen. Okay. Yeah, fine. Do it. If I'll take one question.
I am ready. I have the problem ready with me.
Yeah, sure. I'll take one question only. So if further questions are there, we can do it later.
Okay.
Yeah. So present your question. We'll do it now only.
Because this is means just now what we just hold on, sir. 1 minute. So this is the problem, sir.
Okay. So in terms of federation GRU, okay. The xt is given. Okay, so see, xt is given, which is of 2. What is given is ht is given,
HP is given 3.
which is 3. So based on that, you can say st is also going to be 3. Now y is the
2.
which is of 2. Okay, so this is what given to you. Now
Yeah.
what is the question?
Question is how many parameters in the network?
Um,
Given
that
the
is
GRU process
oh, okay,
sequence,
okay.
total number
So
of
first is what is this process sequence length? What is the number of parameters? So it doesn't matter how much sequence
Yes.
it does process, right? T equal to 0, 1, 2, 3, 4, 5, 6 or
same
5, whatever. Then it will stop and the parameter will not change, right?
Correct.
So based on this, you can figure it out. Let's say how much you will require for u. But this is GRU. Okay, so GRU will not require. I didn't cover it, but it will have one less gate. So just remember that one less gate. We call it a reset and update gate. I don't
So
know
for
if
this, the given the input, will you calculate the parameter because it is not matching for me?
answer might be wrong. Depends.
Oh.
That
So
could be a
can you
missing.
calculate so that I can able to at least know whether I'm correct or not?
Yeah, sure. So
I'm
okay.
sharing once more.
No issues. Okay, so see, first I need to compute any W, U, B, and what else is there? V and C.
B
These
and
5
C.
kind of parameters are there.
Correct.
All of the W's are same, right? So let's say this is related to input, and I'll get another with respect to output. Then there is something
Sorry,
called
sir, are you
ST.
sharing? Are you writing on that?
Oh yeah, I am
That
writing
was,
actually, but
yeah. What you can do is
no
you can
issues.
take a
You
screenshot of the
can
question and
yeah you can stop it. So okay, now I need to share it. Think so. Can I reshare? Okay. Yeah. So from this, we know that we need to figure it out this 5 kind of constant. There is something in st hat, but that is like uh there is like just a timestamp, right? It will not be calculated again. It is like a for a limited period of time we are storing this value. That's what it is. It's not a parameter calculation again. So you'll have 2 kinds of them. Then u0, b0, v and c. I mean, say, yeah, input, right? So this 10 kind of equation will be for GRU. This is for GRU. If it was LSTM, then I would have had forget also this 5 kind of thing. Now I have an input which is going of 2 dimension, let's say. Okay. It's a 2 cross 1. And then I have ST or HT you can consider, which is 3 cross 1. And based on that, I should what will I get from the equation? I need to get ST first. Uh, uh, mm, yeah. So this is related to X. This is related to HT. So X will multiply with U naught thing, and this UI or U naught whatever. This will be with WI. Okay. Now I need to get this OT, right? Which will have how much? Two param. Should it be two? I don't think so. should have.
It should be 3, sir. You've given ST as 3.
Yes, ST is, yeah, it should be ST, right? Yeah, that's
On top you've written XT is 2, HT is R3, ST is also R3. So it should be 2 into 3, and W should be 3 into 3. Or 3 into 2, and W should be 3 into 3. U should be 3 into 2, right?
yes, correct. Okay. So this should be 3 into 2 or something like that. This weight matrix. This should be 3 into 3. And then we
Bias
have
will be 3.
bias will be 3. Yeah. So we have 3 sigmoids in this, and we are doing it. Okay. This thing, because we need 3 as output based on this SHT. I know that I need 3 outputs like this. So there will be 3 of this. So this is for one case. Then I'll have again for the another. Like all this, W naught, U naught will be similar. It will not change at all. Then we have B naught and B1, which is also similar. Then we have V1. So V1 is related to V1 is related to Y.
2 cross 3 will be, sir.
Okay. So yeah, we have Y. So something we have, let's say 3. Then on that I need to apply this thing, softmax or something, which will have 2, right? That's only the way to get a output like this. So again, we should be like
3 cross 2.
3 cross 2, right? And then C should be 2
Correct.
Right, sir.
or something, right? So based on this, you can compute all of them.
So I computed, but my answer is not matching. What is the answer? It's coming for you.
It should be 6 plus 9. 6 plus 9 plus 3, which is 12 into 2, because we have double of this, that is 24. And then I'll have 6
So
plus,
it will be 18, sir. 6 plus 9 plus 3.
18 into 3, 54,
Yeah.
plus 6 plus 2. I got 62, sir.
sorry, 6. This is 6. 6 plus 9 plus 3, which is 9 into 9 plus 9, 18. Okay. This is 6 plus 2, 8. And we'll have double of this, because both kind of thing, and this is also double. So 36 plus 16. This is the right answer. 12, 1.
No, so I got 62. But why 36? Because it is 3, no? 18 into 3. Because you have only one output. So 3 into 2 plus 2. Because you have 3 Ws.
Where? Sorry, where? W's? W's are 3 into 3 only.
No, W's are 3 into 3, but you have 3 sets of that.
No. For GRU, only 2 sets are there. That's what I said, that if it is GRU, we have 2. If it was LSTM, then I would have had forget get also, which we don't have now. GRU doesn't have forget get. It has only 2 gates. Input and output, you can say.
But you still have that plain W, capital W, capital U.
Yeah, for ST, sir.
Okay, sorry.
That is why it is 3, sir.
So it is, sorry, Otherwise, I would have multiplied by 4. Correct.
Yes.
This and
It
then
is 3. So it is 54.
Yeah, this is 54 and this is 24.
No, not 24. Why 24?
8. Sorry, 8 or 16.
It is only 8, no? Because output is only 1. 6
correct,
plus 2.
Sorry. 54 plus 8, which is
62.
Yeah, correct.
No, that's what I got. But actually, answer is given is 113. I don't get how it is coming 113. You cross check. I'll just share my screen. That is why I confused.
So maybe you can post on Discord. The answer might be wrong.
Yeah,
Right?
you can post on Discord.
Oh,
Yeah, correct.
okay.
So
So 62 is the right answer, huh?
yes.
Okay.
You can
And
post
if
on
otherwise, Manoj sir will clarify on Discord. Don't worry.
Yeah. You can put on Discord, okay? If something
Okay.
like that.
Okay.
So this was LSTM. We covered that. So you don't need to do backpropagation of something like LSTM thing because in like RNN we couldn't able to do it. So I mean with pen and paper it's not possible. That is a case. How with LSTM and such kind of thing, how is it possible to do in exam? So not possible. Okay, GRU, which
Sir, can you present your notes, sir?
gated current unit. I'm not presenting. So
Stop
I
sharing
can't
this now.
not sharing.
oh, okay. Uh, stop. So GRU again. I'll just take hit NH is there. Okay, this looks better. This is similar image. That's why.
So in this, can you just go up on your notes? Just one clarification required, sir. Above this, yeah, down. Just below this, sir. Yeah. Here the B dimension should depend upon WF, not UF, right, sir?
Which one?
The B, that
B
bias
should
what you given D cross 1.
should depend on
Should-
the input. Should depend on XT.
No,
Or
it should be on the W. Should be based on the dimension of W, right?
yeah, it should be based on the dimension W. That is correct.
Right. Okay. Right.
So it depends on HT. Yeah, sure. Depends on the dimension W.
Right, sir.
Okay, so this was LSTM. We are here. So in this, like they call update and reset get, but we use input and output get.
Just sir, one clarification. It is means correct me if I wrong. Shall we call it depends upon W or shall we call it depends upon HT?
What we call?
Means that the Vivek asks the question, the bias term is depends upon W. Shall we call that depends on W or that depends on HT?
I mean, the dimension of that column, right? That vector will be like similar to W. So whatever W has it. So but it comes from HT, right? I mean, see, we had this many inputs going there. So So that's why, and how many sigmoid neurons are there? It depends on that. So that's how this biases come, right? This depends on the sigmoid neurons actually, and
But
how
this
you
sigmoid
come up with.
neuron is lies with the HT layer. W is the just weighted matrix is multiplying and giving that HT.
Yes.
So bias term we calculate the input. It's means it's going towards where? It's going towards HT or it's going towards W?
The bias.
Yeah.
Oh no, bias goes to all three of like this is a sigmoid, right? Let's say something you get here, let's say 0.25. From this you get 0.5, and then bias is let's say 0.33 something. So this will add up, and then you apply sigmoid over it, right? So you'll get a value out of this, and it could be in form of vectors. So this will be in form of vectors, like all three of them. So you'll add all these three vectors, right? So this is from B, this is from UX, this is from WHT minus 1. So these three vectors you'll get, you'll add them, and based upon that you'll apply this sigmoid over it, right? Means this vector is coming because we have a layer of this sigmoid neurons, right? So this neuron, each what do you call row, you can consider as output of that sigmoid neuron. So I mean that's how this computation goes. Okay, fine. So now what is GRU? Let's just so I'll not go much into this. You get this is the again architecture of it. That's how it's being made. That you understood LSTM. The same equations are there. Some different, like we don't have one less equation, but that's what we do. We compute sigmoid. We have okay, here it's not written, but we get something like ST minus 1, and then we get XT. We don't have HT minus 1 now. Like we don't have that. We have only two kind of inputs, and we get this. So what happens is we go here, we apply sigmoid over it. Again, we see the same thing is going there.
Sir, excuse me, sir. One request. I think in the previous one also I had this confusion. When you are saying here, can you just mark out what portion you're talking about? Because your pointer is getting lost within that image. It's difficult to figure out where that here is.
Not here means
Yeah,
I mark, right?
yeah.
I mark it.
Yeah. The
Okay.
marks were not visible earlier, but yeah.
Okay. Maybe I'll use another. Okay, red, no red.
Yeah, yellow is fine.
Yellow is
Yellow or
better.
blue or
Right.
anything. Yeah, that
So
would be
this
fine.
XT is going there, right? I mean coming to this first sigmoid. This sigmoid I'm talking about. It's coming here. It will produce some output. Similar XT will go there. Okay. It will multiply with it. Okay. And I don't know that this shouldn't happen.
Basically, we're taking sigmoid and multiplying it with itself, right?
Okay, sorry. Sorry. See, it's going there, and this going there. So this two inputs are going into the sigmoid. ST minus 1. So first ST minus 1 is going, and XT both are going into this sigmoid. Okay, this first sigmoid. So this two kind of inputs are going there. One is from here, and then this XT is going there. It will have element wise multiplication. So this thing you can consider element wise multiplication. Then you get some output. So this is what like written as ST, this kind of symbol, right? Then what happens is both of them, like ST minus 1, and both of them will go here in the next neuron. You'll get some output. I think you okay, this GRU is not something we cover. We feel that because we never do this subtraction, right? Or we do it. Yeah, it seems we do it. Yeah, sorry. So what we do is we subtract 1 minus this whatever comes from this one. We do it. So, and here st minus 1 is coming there. We multiply it, element wise multiplication. Then okay. I mean, just try to figure it out. It is really hard to explain for now. But basically, you figure it out. Depends on the equations, which will come into the quiz, right? We don't have much time. That's why. So I'll write the gate equation, which is xt plus b naught. Then I'll have it, which is segment of wi s t minus 1 plus q I xt plus b0. So this is for this two sigmoids, and why do I have not that one? There could be something wrong with this image as well, right? I mean, there are several variations of gates present, but whichever we taught is a little bit. And this st minus 1 plus uxt plus b. Okay. This will go into sigmoid. Then I have st. Oh yeah, third segment could be for the 1 minus it st minus 1 plus it, and this is st. Right. Okay, so this is the equation. For this, you have to figure out how many parameters are there based on the input and all. You can do that. So that's what is on GRU, and what happens is, since we now have this, see, this long-term memory is there, right? This thing is going on. This long-term memory is going on. You can kind of feel that even if we lose something while doing back propagation, let's say vanishing gradients happens, there's another component coming up which will not let it vanish. Or while doing back propagation, we don't put. Let's say it didn't contributed while going forward. Why it should be dependable when we go back, right? So that's why we exclude them, and something we do, and that's what helps us in not happening vanishing gradient, right? So these two are helpful for vanishing gradient. It resolves the vanishing gradient problem. That's why we need this. Okay. Exploding gradients you can handle easily by clipping it, right? So clipping means you set it some rule that it should not go beyond 3 or something. Anything you can set that gradient should not go beyond this value. So exploding gradients you can resolve using the clipping, right? So clipping you can do. Yeah.
So, I have one question here. Can
Yeah.
we use clipping for the vanishing gradients also? Clip it to a
No,
certain.
not required. Not required,
Okay.
because let's say vanishing is there. What happens is 1, then let's say 0.8, 0.2, 0.001. Now what will you clip? Like, there is nothing to clip, right? Clipping means it will not increase it. It will only stop it. But from where they are going to 0. They are not even even if they are going towards negative, that was also okay. It's a -3, -4 is also okay, because some direction they are giving, something they are giving, but 0 will not give anything. So 0 is the issue, and that's why we don't do clipping there. We only do
Why
we can't
why
do
why I'm asking is because one of the PYQs it was giving that vanishing gradients through
uh
clipping, and
correct,
that was uh, shown as correct. So that's why
correct,
I'm
correct.
asking.
Yeah, I know, because you have put it somewhere.
I probably didn't, but someone else would have put it.
I posted it. The answer is incorrect, is what the instructor said.
Yes, yes. Yeah.
Okay.
Okay. Yeah. Somebody. Yeah. Sorry. Somebody put it there.
Sir, one question.
Thanks, Anubhav.
Sir, one question, sir. In
Yeah.
RNN architecture, we had ST as the state variable.
Yes.
in in LSTM we have both ST and HT, and I don't know why I'm asking that. In GRU we largely stuck to ST. Right?
Correct.
Now, what is the output of this module? Like, is it HT? Because in the slide somewhere it says LSTM, it says RNN out is HT. Here GRUST. So what is the vector which is going out, which feeds to the final layer? And what is the final layer? Final layer will still be that YT is equal to softmax. Does the I'm assuming the final layer doesn't change versus what it is in RNN. It's the same thing, except that the HT calculation or ST calculation now is more elaborate with all these gates and states.
Yes, yes.
So what is the output of LSTM in this case? It's HT, which is another way of representing whatever state variable, whereas GRU we are saying ST. So is there a difference? I mean, do we have to worry about HT, ST? So that is one confusion I have. And I'm assuming the final layer is exactly same as the RNN.
Correct. No, not final layer. No. So nothing of this is of RNN. We are not doing anything, let's say, recurrent in this, right? If we do back propagation, it's simple back propagation like sigmoid derivative of sigmoid. That's all. We don't have to. Sorry. I mean, unless you go from one LSTM to another LSTM, like this is a time step T1, then another LSTM will be connected to this, right? That's when I mean connected means a similar thing. It will go back again here, and you will get so that's where you will do the this time wise back propagation. Inside it looks like similar only, very simple kind of thing.
Okay. No, what I mean is from here. See, what are we getting in LSTM as an output? HT.
In LSTM, so this thing will be there, which we get, which is ST, which will feed to V, and we'll get output from this.
So we get two outputs, sir.
Yeah, we get two, but the second one HT, we don't use it for predictions or something. We will just feed it. That's all. This is short-term memory.
Okay. So the ST is what we because the slide says RNN out is, I don't know why it says RNN out HT. There is something in the slide. I don't know what that means actually. So I thought maybe it connects back to how an RNN connects. So I don't know. As if anybody has figured out. So ST into V will give the YT, and then you do the softmax and you get the output. That's what
correct.
Okay.
Correct.
And
HT is just there. It's a short-term memory which will use to update the gets for next term. That's all. Like this will help in
temporary state.
Yeah.
Okay. ST is okay.
Okay. Fine. So this is on LSTM and GRU. That covers week 10. So I think Krishna is there. He will cover transformers. Krishna, are you there?
Can you hear me?
Yeah.
Okay, so I'll just So I mean, this is, can you also see the screen?
Yes, the screen is visible.
Okay, in that case, let's just go over, we'll just go over two things. We'll go over encoder decoder model and revision, right? And we'll just quickly go over encoder, decoder, and attention and transformers. We'll very quickly go over this. I think most of you have also attended the live sessions and we discussed this quite in detail there. Right, so let's just see what is what is the job of an encoder? Encoder will try to uh, uh, from whatever is your word representation, it will try to get you to the uh, vector representation, right? So every time, I think this lecture, there was one, uh, basically what all were covered. One was, okay, one was RNN based encoder, the other one was, let's see. Right, so I mean, just now you have all seen um, the equations for RNN, right? So for this lecture, we will just look at the abstracted version of RNN, and right, whereas same thing even with GRUs and LSTM. What do we cover exactly? So I'm thinking I'm trying not to have this overlap with the live session that we did, but what is the new content that we can cover? I think that day we did not discuss so much about the applications part, right? So just to remember a few things. Yeah, just confirm you guys can hear me okay, right?
Yeah, we
So
can hear you. I think what you had talked about that time was that you will take one or two numericals and expand them to a model, just so
numericals
that
for
we.
what? No,
So I
I
mean, I
told you
don't.
that numericals for LSTM and numericals for these attention based is not. I think we ran through an entire example, right, last time. And numericals for this is anyways not going to be there. I mean, there is no way that you can solve attention numerical using a pen and paper.
Sir, if we can revisit that calculating number of parameters, that would be great.
Okay, okay, yeah, so we can do
Specifically
that.
for the decoder, sir, if we can do it for the decoder. The encoder part you took last session.
So the encoder part was mostly clear, right? Just
Yes,
as
but
a,
if
Yeah,
someone
encoder
has
was
doubt,
good.
yeah, please, yeah, go ahead.
no, I'm saying if anyone else, I was clear on the encoder. The decoder, I have a
I
lot of
think,
problems.
yeah, encoder we went quite in depth there. So, and wait, so just for the sake of completion, let me at least cover what attention is. I mean, if nobody wants to cover attention, then we can even skip this. Well, it's already 8:30, I believe, right? If
Encoder and
attention is,
attention was very clear, sir, last time.
which one?
Encoder and attention was very clear last time.
Yes, sir.
Okay, if encoder and attention was very clear, and for those who have not seen the live lectures, you can please go ahead to see those. And if there are no, if I mean, if there is no interest in attention, then we can just move forward. Right, we'll just wait for a few seconds. If somebody wants to, I mean, I'll just write this basic attention thing, right? We said V transpose some nonlinearity U st minus 1 plus W H J. What is happening here? All these are attention parameters, right? W A G. We said this is coming from some RD. This is another matrix. This is another matrix. This could be some. If this is RD1, this is RD1 cross D, RD1 cross D. These could be from RD, RD, and so on, right? And what does this finally give us? It gives us A between T minus 1 and J. And finally, we take a softmax to get alphas. I hope this part was clear, right?
Yes, sir.
Right? You take softmax over all different A's, different pairs of A's. Okay, so I think we covered this in detail in the live class. If this is also clear, then let's move on to attention, then transformers, right? Transformers, I think one thing that was important to understand is even from example, or at least you guys should understand why were transformers brought in. Why did we not just settle with sequential LSTMs and RNNs? Right, and what are the different reasons? Again, we discussed this quite in depth, trying to motivate what are the reasons. Why should we think of transformers? Right, so let's just go in the encoder decoder for transformers. Right, where is it? Do you guys just want me to do the decoder part? I think we can just go in depth on that, right? Or at least do you understand this self-attention mechanism? Right? This also we covered quite in depth. Like I think we spent 1 hour understanding this.
Yes, sir.
Self-attention mechanism is clear, right? And how is it different from this? Here, these are coming from two different. This is coming from encoder. This is coming from decoder. And so these were called as cross-attention. Right? But whereas when we want to parallelize everything in the case of transformers, and so we go ahead with self-attention mechanisms. What does that mean? It just means that I might have several words and I want to find the importance of the word among themselves, meaning this one word is a weighted summation of the other words. How did we do this? We parameterized this whole scheme using three matrices value, right? So can anybody tell me what are the basic things here? Remember, so I mean, you can very intuitively remember the formula. One thing is you can just say that if I want to find the importance between two things, I'll simply take their dot product. But then we realized why this is bad, right? This is just taking similarity between those two. So let me just take the let me just take a linear transformation and then take a dot product. So this becomes, anything can be, like, let's say this becomes the key and this becomes the query, right? You can do this, or I think even the other way, doesn't matter. Like this could have been, this could have been the query, this could have been the key, right? This is one way to say how important is query with respect to key. And then finally, we are saying that each value is weighted summation of values, right? What are values? Values is again just here. Now these will give you A's. You take a softmax, you get alphas, right? Softmax over A will give you alphas. You take a weighted summation over these values. How do you get value? You just multiply this, right? I hope this part was clear, right? And we had intuitive explanation of why these three matrices are used, what is the importance, and so on, right? And how all of this could be parallelized. If I could simply write them in the matrix notation, that would mean something like this. And there was a coefficient here, but I mean, not so important. But I hope everybody understands the intuition behind this formula, right? If not, then please come forward and we can discuss.
This is clear.
And there was a natural extension to this idea. Multi-headed attention, right? So can anybody tell me in one word, what does this mean?
Basically,
We are just expanding the scope of attention, right?
multiple self-attentions to focus on different parts of the data.
Right. So you simply replicate the self-attention block, nothing else, right? You have one block, you have two blocks, you have three blocks. Finally, what do? How do you manage? How do you
You concatenate them
you
and then you
concatenate everything together. And finally, see, you have to be careful in this part when you're concatenating the dimensionality of the vector should be such that it can be fed back again, right? So remember, and if you even see the lectures, Professor Mitesh has sort of given you given a very nice explanation on how many number of heads, then you just divide it by that, you later concatenate it and then feed it to a feed forward network, right? I hope you guys remember this, right? We just did this like 2 days back.
Yes, sir.
So I think most of you are interested in the decoder block, right? So we can go ahead with that. Let me see. Should we bring back the figure that we used that day, or we can just go ahead with, let's say, so I'm just drawing one single decoder block, right? And this is while actually this is not there. So we said that go, I, like, DL. This one should give I, like, DL, stop, right? And we said that there is some embeddings coming from the encoder as well, right? So E1, E2, E3, right? I hope you guys remember this, right?
Yes, sir.
So what were at a higher block level, what were the at a higher block level, what were the components of a decoder? You had a self-attention. This was masked, right? Then there was a cross-attention, and then there was a feed-forward network. We remember this part, right? Now we want to go in. Do you want me to go in depth of each of these, or are these architectures also? Because I'm just asking this because we discussed like 2 days back.
Not so much how it works, because I think that you did it last time also, but like a lot of us are struggling with estimating parameters. I'm speaking for everyone else, but they can chip in.
Yeah.
There's particularly one problem from PYQs which is circulating. So we're not very sure how many W's and Q's are there from the cross.
The number of parameters, but I think we worked out, but that day we worked out something that was for the encoders, is it?
Encoder, right, sir. Decoder is not clear.
So if you guys might, if anybody can share the screen, and then we can go ahead at least with what the problem
the question is there in the chat if you want. It is there.
There is in chat. Okay, let me see. Because the thing is, I've joined in through an iPad, and it is hard to navigate. Can any of you just share your screen?
Yeah, I can do that. Let me just open it.
Yeah. But conceptually, you guys are clear with what is masked self-attention, what is cross-attention in the feed-forward network. Feed-forward network, FFN, you can forget, it's nothing. It's a simple MLP. Cross-attention and self-attention masked version should be conceptually clear.
Can you see the...
Yes. So consider a transformer model with the following specifications for the decoder part. Input is this, number of heads in this, head output dimension is this, dimension of feed forward is this, number of layers in the decoder is this. Okay. Assume that each decoder layer contains a one multi-headed attention mechanism for self, one multi-headed attention for. So you see, so the first part is, after this, assume that each encoder decoder. The first part is the self-attention masked version. The second part is the cross-attention. Then the third part is a feed-forward network. Right? No bias is included. Calculate the total number of parameters. Okay, I see the problem. Now, do you also go ahead and want to show whatever solution you have done, or can Vasu show whatever you guys have tried out, and then we can at least reason from there?
It's very messy. I don't even know.
I understand.
Yeah. Have it somewhere. I mean, I know we tried Vivek, but I can't recall where we have it.
I can just tell you what we did, sir. For the
any chance that you show us how you did it?
I can repeat it out. We can memorize the question and go back to your this thing. I can repeat what I did. I can't. I don't know.
Okay. Let me just see the number of heads. Okay, but some of you have the question with you, right?
Yeah, we have the question. We have the
Okay,
question.
if you have it open with you, then let's just see. Can
Maybe
you
you can take a screenshot if you want.
You take a screenshot from Anupam's share and then put that screenshot onto your
Yeah,
writing
yeah, yeah.
application.
Let me just see. In just a second. So now. To 10. Okay. So can you still see the screen?
Yes, we can see the screens.
Okay, so in that case, I can see both of them, is it? Okay, so anyways, input 20-dimensional embeddings, right? Embedding input is this. Number of heads in self-attention mask is 2. The head outputs a 10-dimensional vector. The dimension of feed-forward network is again 16. And the number of layers in the number of layers within decoder is 3. Yeah, now let's discuss what you guys did and we can debug from there.
So for the first layer, I took the input
See,
into the...
just for the first layer, right? Whatever happens, you just multiply it by 3 later on, right?
Yes, yes.
And again, we are just talking about one head because when we do it for one head, we just multiply it by 2, right?
Right, right.
Okay. So now let's see.
So
Yeah.
the first layer has 3 sublayers.
The first layer has 3 sublayers, okay?
Any layer has 3 sublayers. So the
That's
first
right.
one is
Yeah.
the self-attention mask.
Yes.
Self-attention mask, I'll do the input times the
Input,
head output
right? So the input is of
into
dimension 20,
20 cross 10
right?
cross 3 because I'll be taking care of those 3
Okay, right.
query.
So there are these W query, W key, W value,
Right.
right?
The
So
the only thing here, sir, because there are 2 heads, should it be 20 into 10 or 20 into 5?
okay, yeah. Let's figure it out, right? So let's see that. So what we are saying right now is I am feeding in a 20-dimensional embedding, and the head gives me an output that is in 10 dimension.
Right.
And I am saying that there are 2 heads.
Right.
So I
When
mean,
I concatenate, I get 20.
my first observation is that is already taken care of, right? If I
Right.
concatenate 2, 10, 10, 10, then I get 20.
Right, sir.
Right? So the head output is 10. So I would just say this is 20 cross 10 cross 3. Right? This is for each layer. This is taking care of WQ, WV, WK. Right? Can
For a
we all
single
agree
head.
on this?
Yeah, that's actually that 2 into 10 adds up to 20. That is a neat one. But it has to add up to the final output. Okay, that's a good one. Yeah, this is clear, sir. Go ahead, please.
Okay, now let's go ahead. So what happens after this, right? Now again, in this one again, you feed in, so this is the cross entropy part, right? Cross entropy part, what happens in cross entropy? What parameters do we have there?
Cross
We have
attention.
another set of W, we have same, right? Here we had 1, 1, 1, we had here 2, 2, 2, right? WQ2, WK2, and WV2, right?
It'll be cross attention, sir.
Oh, yeah, sorry. Yeah, you're right. Cross attention. So this is fine, right? The same set of parameters that we had here are also occurring here.
Right, sir. 20 into 10.
So how about we do this into 2?
Right. Now, here I have a doubt, sir.
Yes.
One is that we are assuming everything is unmasked.
Yes.
Then it is right. But if we say only 5 words are, only the 50% of the words are there and 50% is masked, then how do we do it?
Does the question say that?
No, it doesn't.
No. So see, the mask does not really see. Mask is more of an engineering detail. Mask is you being smart as a programmer to remove any future information from the model, right? Does not affect the number of parameters. Whatever attention you calculate, you calculate. Whatever parameters you need to calculate, you require them. All you do is you zero out your alphas,
Okay,
right?
sir.
So I don't see how the number of parameters is going to change. Whatever you calculate, whatever are your alpha 1, alpha 2, alpha 3, alpha 4, if you're at time step 2, you'll just zero out these two. That's it.
So, yeah, sir, one question in
Yeah.
when we're moving from self to cross attention,
Yes.
if we concatenate the heads, then it should be 20, right? Not 10.
Then it should be 20.
Because there are two heads, right? See, when we are moving, see
Right.
the output
So
of
there are two heads for
self-attention.
self-attention. That's right. So you already, that's right. So whatever you get is again a 20 here. Okay, let me just draw this better, right? So whatever was the self-attention, there are two heads here. This gave me a 10 dimension, this gave me a 10 dimension. Finally, what you get is a 20 dimensional I mean, you just concatenate and you get 20 here.
Correct.
Which is the same as what you were getting here.
Okay. Got it.
Right.
Got it. Clear.
So cross attention, and I think all this is just with the hope of being consistent, right? So if you feed 20 here, so that's why I said that we can just, so for the sake of
you're just doing it twice, multiplying it twice. Got it.
Yes, I'm just doing it twice, right? And then what's the final thing? Also notice that we have
No,
not
I'm not
yet.
clear on this, sir.
Which one?
You have put 20 cross 10 cross 3 cross 2 for both the attention, self-attentions layer.
Yeah. So actually, let's not write. Okay, let's just do it here, right? So let's not write any short forms, right? This is head 1 and this is head 2.
Right, sir.
This is 20 cross 10 cross 3, 20 cross 10 cross 3.
Right, sir.
Right. And then encoder, you have just one. Right? So this is 20 cross 10 cross 3. This is the cross. Sorry, this is the cross attention.
Cross. Okay.
This is the head 1 of self-attention. Self-attention. Right?
So can you just multiply the heads by 6 instead of 3?
Why so?
The cross and self-attention, the parameters should be the same.
Can you say that again?
So the cross attention is also 20, 10, 3. Self-attention is also 20, 10, 3.
Yes.
And this recurs. I mean, it is not like the cross attention dimensions will be different than self-attention dimensions.
So why 6? Why 6?
I mean, 20 into 10 into 6.
Oh, I mean, okay, you're just simplifying the algebra, is it?
Yeah.
No, but the purpose of this is to write it in as much detail, right?
No, I agree. I mean, absolutely. This is what I wanted. So please continue the model.
You
That's
see,
not
we
an
were
issue.
trying to simplify it here, but it's not so clear, right? So then,
Okay.
what does it say? Then we are saying that finally we have an embedding. Okay, so this is problematic, right? So we are saying that the feed forward network. Can you just go back to the word? Can you just repeat the wording of that one sentence? The feed forward network.
The dimensions of feed forward network is 16. One feed forward network. That's it. Those are the.
So again, the output here will be of.
So it's a multi-headed cross attention.
Yes.
Yeah. So, but the attention blocks will concatenate then it will be just one output which will go into the feed forward network. So you don't need two feed forward networks. You just
No,
need
no, that is fine. I'm saying there should be two cross attention blocks.
Oh, does it say that?
I mean, it says multi-headed cross encoder decoder attention.
So let me just think, because I think after self-attention, you automatically do concatenate, right? So do you again do a... No, I don't think so, right? You're saying that this cross-attention should also be repeated?
And I'm not saying that. I'm just saying that in the question it's written one multi-head attention mechanism for self-attention and one multi-head attention mechanism for encoder-decoder attention.
no
So
that see that cross attention is called multi-head, if I'm not wrong.
no. Cross attention is encoder-decoder. It's a cross between the encoder and decoder. Multi-head does not have anything to do. But
Okay, let's go ahead with this, and then if what you're saying is right, then we'll just add this one more time to see what they mean, right? So
Right.
I am guessing that the feed forward network is 16. So that means it is taking input from 20, right?
Yeah.
In 20 dimension.
Right.
And it should give me something in 20 dimension, right?
So
Right.
20 into 16 plus 16 into 20.
Yes, that's what I meant. So 20 into 16 times 2. At least we can simplify this, right?
Right, sir.
So then can we just sum this up?
sorry to interrupt again, but again, this won't work, sir, because if you just take one cross attention, then it would be 10 into 16 plus 20 into 16. Because
10 into?
eh, because of the cross attention, we have taken 20 into 10 into 3, right? So the output of this would be a 10 dimensional vector, or it would be of 10 dimension. So if we are taking single cross attention, then it would be 10 into 16 plus 16.
I see what you mean. I see what you mean. Yeah, right. You're right. You're right. So you're saying that, so the question says there are multi-headed cross attention also?
Yes, sir.
Okay, I see. So in that case, how about we do this?
Sir, can you repeat this part? I did not get whatever just happened.
Yeah, let's just first see if what we are calculating is right. If it's wrong, then no use explaining the wrong thing, right? Let's just go ahead to see if this is right. So
Okay,
is
sure.
this right now? I think so. So again, here now this will give us 20, right? Actually, you're right. So I don't know if the output is 10, then this could have simply been 10 cross. Okay, let's calculate. Anybody who can just see, this should be easy, right? So this is 10.
The cross attention parameters, will they be shared or will they also be calculated
No,
separately?
when they say different number of heads is like independent. So you don't have.
So there is
No, the cross attention input will not be separate, right? Because it is still the same context coming from the encoder. Why will that be different?
So just a second, 64, 640. So how much is this? 4 3s are 12, 12 2s are 24.
2440.
3040, sir.
3000. Oh, sorry.
How much? So
640.
24 plus 640, right? Into 3. Because how many they said that the layer
Yeah,
has
3
3.
layers, sir. 3 layers.
So is this anywhere
9120.
close to correct or we are wrong?
way 3 times the number, roughly 2.5 times the number.
So
The
we are
answer given
2.5.
is 3680.
3680.
So that
Yes.
thing is, but we're not able to arrive at that number any which way. Any combination and permutation doesn't take us there.
I think this 9120 Pritam also put out on the chat box long ago when we started working on this.
I see. Okay. So any suggestions on what can change here?
So in the
But
diagram,
in the slide, there was this one other vector.
yeah, W0.
If you want, I can share my screen and show it.
Yes, please.
try to follow this, because they give some rough estimate of the. So the input is 512.
Yes.
I'll just let you be here. So
Yeah,
this
yeah.
WO1, WO2 additionally, right? So I don't know where this WO2 and WO1 is coming. With
No,
some
no, I think that W is just saying that they're trying to explain you the concept of mask, right? So that's coming after semicolon. What that means is function of something
yeah. So
given something.
okay. Uh,
But they're adding to the parameters also, sir, here in the slide.
Okay, let's see that.
they're
Okay.
adding this something like it's like input into input.
Oh, WO1, right? Okay, where are they adding WO1?
Yes. WO1, 512.
No, they're calculating fine, but where are they adding it
No, but
somewhere?
eventually, when they say 2.65 million, they're adding all this. Like these are all parameters only, number of parameters calculations. So I'm guessing WO1 is also one of the like the
Okay,
contribution.
so when they said 2.65 million, then so much has gone within that million, right? So we wouldn't know if they've added this 200,000, because you see 200,000 is already gone into decimals.
Correct, but I'm saying if it's on here on the slide which says number of parameters and they spelled out, I assume that it is part of
Okay,
the
okay,
parameter.
yeah, let's then think of, okay, if you, okay, then what is WO1?
So in our case, it should be 20 into 20. If I mean,
What does that mean?
I don't know. I don't know.
Yeah, but no, yeah, I mean, I would really, so I mean, I generally go with the basic concepts. I'm not very good at like exactly following what's there on the slide, right? Because um, you never know. This is not a textbook. So, I mean, any ideas on what anybody else, if
What is the
they have an
final
idea?
answer? What is the final answer, sir? Sorry, guys. What is the final answer? So I can't see it.
3680.
3680. Okay.
So now here,
3680.
sir, I just have one suggestion here.
Yeah.
So there are two intents here for the session, right? One is to understand how to approach the questions in an exam environment. The second is to understand the concept. Of course, the
Right.
concept we are all going round and round a bit because of these additional things, because they were not covered by the professor in his lectures. So, but from an exam concept, how should we approach this? At least if that part can be clear, then we know that okay, we have our frequency is matching with that of the instructor. We
Right.
should not go and
So,
solve something there which you guys think are thinking differently.
did you understand whatever we solved, the version that I was trying to solve just some time back?
Yes.
So,
I mean, I can't speak for the others, but yeah, I understood you.
so that is the conceptual understanding that we have about the model, right? There is no way to find out how was that number arrived at, right? 36.
Yeah, we can drop that. What I mean to say is that if we come across this question from you,
Yeah.
in the paper, this is the way to approach it. There's an encoder part, there's a decoder part. If there's a single head or multi-head attention, this is what we're supposed to do. If we do it like this and follow the basic understanding that we
So
have.
let me ask. So Manoj, are you there on the call?
Yeah. Hello. I'm here.
Yeah. Manoj, can you? So I tried solving a question, and so this is the number of parameters in a decoder, not encoder, right? Encoder, people are clear because I solved an
Vasu, can you
example
stop
last
sharing?
Yeah. No, I had one more question regarding this on decoder. I'll come back to it.
Can we just finish what
Yeah.
Manoj is
I'll
going
come
to
back
talk?
to it. I'll come back to it.
So, no, you stopped sharing,
And you
right?
will
So I
have to
wanted
share your
Manoj to, no, I wanted Manoj to just look at that question and if he can take a attempt on trying to.
So should I solve? Should I share my screen
No,
and
no,
show the
that's
question?
okay. I have this link in the chat.
So can somebody just tell the question number there?
101. Now it's just image, I guess.
Yeah, it just goes directly to the slide.
Okay.
Yeah.
Are we overshooting the answer on the paper?
Overshooting as in?
The number of parameters that we are
Yeah,
calculating
by
isn't
3 times. We are overshooting
By
by
3
roughly.
times.
Yeah.
So yeah,
the,
so
yeah, sir, go ahead.
I mean, the doubt is with the cross attention part, or
How do we
In
solve the
general,
decoder
how are
part?
they?
How do we
It,
solve it, sir? Because
the,
we are not going by the answer. The answer obviously is wrong in the paper. So we just want to understand the concept about calculating this parameter. That's all.
There is one thing in another paper, I might be in the same paper, but there is one question about encoder RNN, and there in the parameter calculation, in the answer, the W matrix is ignored for some reason. So if you add the W matrix hidden size into hidden size, if you add it to the final answer, I mean, if you minus it from the final answer, you get the correct answer in the paper. So I was just wondering if we are conceptually missing out something, or
So, like, problem we are fitting the answer to whatever is given, the approach to the whatever answer is given here. In the exam, how are we going to do this, right? We all need to have some common understanding of what we need to do.
right, right. That's true. Let's just see if there is a way to, or if, let me just ask Manoj, right? Manoj, like, is there a way, or do you want to
It's like,
attempt?
even if we assume, I know we don't have to force fit, but even if we assume that they made the obvious mistake of not multiplying it by 3 times because there are 3 layers,
Yeah, yeah.
even then
Yeah,
also
then how are we, how
one
off are we? Like, we had to
about
multiply
about it's not very off.
3040.
We are getting
We
3040.
have additional 640 parameters in every layer. So we are
And
off
what
by
they have?
1920.
No, no. So we got 3040, and what is their answer? 3690.
3680. 3680, 640
3680.
additional per
I
layer.
see. Hmm, 640 is it? So this is like 64, which is like 16 times something. Are we missing something on the feed forward network? But they've said clearly said no biases, right?
Yeah, no biases, sir.
Hmm,
So
yeah,
if
even
conceptually you're saying this is the way to do it, then we'll go by that only. I don't think we should try and match the answer because the answer is way off. And but if conceptually this is the correct method, then we'll go by this method only.
Actually, there are so many errors in the last paper in the answers that all my concepts have gone for a toss. Just trying to match whatever I'm doing to the answer. It's become very
no, no,
problematic.
that's not a good way to learn, I would say. I mean, if you're
No, I agree with
backtrack,
you, but what do I do? So that's why I was saying that in this case, we want to understand the approach, not the answer
let's see,
part is
number
okay.
of parameters in decoder of transformers. I mean, generally,
While because we are running late,
yeah.
while Manoj sir is looking at it, can I ask you another question related
Yes,
to
please. Yeah,
if,
yeah, sure.
if guys, should I go ahead? Should I ask?
Yeah, yeah, please. Yeah.
Yeah.
So it's the same.
Are you sharing the screen?
Yeah, I'm sharing the screen.
Okay.
So here,
Yeah.
this concatenation which you had explained, right, sir? Here,
Yeah, yeah, yeah.
right? From this, actually, it's not a you have to go to a feed forward network, right? Like, for example, I mean, after the multi-head, you combine and then you go to the
Right.
feed forward, right? So that is
Yeah.
missing here, right? I mean,
Yeah,
that
yeah, that's missing, right? After that, there has to be a feed forward, and that goes to a linear
yeah.
finally.
So that was I got confused. I thought, hey,
Yeah,
this is a different
yeah, right.
architecture altogether.
Yeah, I
Okay,
think
got it.
like people very often replace a feed forward network with the linear. So, what's the difference between a linear layer and a feed forward network?
Linear,
Any suggestions?
A feed
linear
forward
would
can
be
have non-linearity activation.
That's right. So linear is just matrix multiplication, whereas feed forward network will have at least two linear layers with a non-linearity in between, right? Yeah, that should be there.
Okay, that was the question. Then after everything is over, just one last question on parameters in CBO. That will come to at last if you have time. But that's it. I'm done.
Okay, sure. So
Thank you.
we'll see if Manoj is able to. Otherwise, at least we should clarify, right, how this is. It will be great if one of you can also please post this on Discord so that we can. Let me
It
just see.
has been posted actually.
Oh, really? Okay.
I did post
So in the lecture
Yes.
that in the slide that W0, yeah, is it something called projection matrix? That means when we are concatenating these two, we are projecting something and then we are taking that projection input as to the feed forward neural network.
Good thought.
Yeah, so projection matrix, why would we need it? Because just to bring it in the right dimensions, is it?
Well, at least it's not covered in the concepts in the lectures. I can't remember
Right.
any projection matrix being used.
So if we take that matrix out of the parameter calculation, does it come correct?
No, because we are short of, when we are not in excess, we are already short of parameters. So we need 640 more.
Can you present your screen again, Krishna?
Present my screen again.
Yeah, that where you solved this.
Yeah. Just a second. Yeah. So,
Okay, so
I mean, this is the decoder.
yeah, correct. So we have this two self-attention blocks, okay, which will give what 20 as output, and then we have two cross attention also, right, which will give again 20. Then feed forward. So okay, what is the issue then? I mean, not.
So,
So this is 20 cross 3. Okay, 20 into 10 cross 3. Okay. Then again there also it's same.
so see, what we are saying is a 20-dimensional input went here and a 10-dimensional
Sorry,
output
just I
came here.
lost my connection.
20-dimensional input came here and 10-dimensional input came here, right?
Yeah.
So we need three matrices, WQ, W value, W key. So that's why this 3. Right?
Yeah,
And
correct.
then we
So
concatenate these two. So we get 10 and 10, we
then
get again 20.
correct.
So then we again feed cross attention, we feed 20.
Yeah.
And again, we again have the key query value.
Yes, correct.
So again, so they are saying there are multi heads of cross attention. And so
no, right? In question,
Single. There will be
one
again a single one
multi-head
only.
attention. One multi-head attention. So multi-head have two heads, but it is one only. That whole thing.
So
even,
this you're saying,
even then the parameters will be the same, because then you have to do 20 into 20 into 3, because the output has to be 20. It will work out to the same. I tried both.
No, 20 into we want output as 10, right? So 20 into 10 into 3 is correct at cross attention. Then another is also correct, right? 20 into 10 into 3. 20 is going inside. We want 10 as output. So again it will be same. So that is correct, right? So up to cross attention it's correct. No?
I see. But then I think there is a mismatch in the answers.
No, wait. So when you do feed forward layer, right? So
Yeah.
let's say you have 20 of output size, right? Then what you do is you first put a hidden layer.
Right. So that is of 16.
Yeah. So that 16 hidden layer. So once are the weights which are go into the hidden layer, and there will be another which will come out of hidden layer. Like there will be two kinds of weights.
Right. So that's why. So this will be
one
20
more
cross 16.
Yeah.
This will be 16 cross 20, right?
Yes.
So that's why we have 20 cross 16 into 2.
So okay, then it is correct, right? So you got 1200 plus 1200. I mean, here you got what you got in. So how many got you in first layer? 1200, right? And then in cross attention you got 1200 again.
Yes, 1200 here, 1200 here, and then here we got
320 plus 320.
640. Yeah.
So that is the summation of 1. How much it is? It's going to be.
This is 3040.
40, yeah, 3040.
Yeah.
And we got 9120. Yeah, so that is the correct answer. That is the correct answer.
Okay. The paper had 3680. We were really way off, so we were wondering.
Oh no, 9120 is correct. So I see that is there. I mean, I confirmed with the previous instructor. It's a mistake by them, but this is the correct solution, which is presented 9120.
Right. So we were doubtful because I think the answer in the sheet given is something here 3680.
No. That is incorrect. In last term, they missed this part of. I think one more. I mean, first they missed that there are 3 layers, hidden layers. They considered 2 only, and there was some other mistake of something related to feed forward, that FFN part. So that's why.
So, but this part is correct, right? 9120.
Yes, that is correct. 9120 is correct answer.
In that case, then you guys can just have this figure in your mind and how you can solve it.
Yeah. This is correct.
Thank you, sir. This is very helpful. I mean, this is what we were looking for when I said a model. At least there's something which you can visualize and then try to figure out.
Would it be possible to put this on Discourse as well, since there has been a thread raised on this?
Just this image, sir.
Yes,
You want this image?
Yeah. Actually, we can take it. I can.
Yeah, you can just somehow take a screenshot, right?
Yeah, this 1 second. I'll just take.
Yeah, we'll post it on Discourse as well. Krishna will do that. Not an issue.
Okay.
Yeah. Share me if you can't.
Yeah, sure.
Sir, 2 very quick questions. If you're done with the theory, I'll ask. Otherwise, I'll wait for you to finish.
Yeah, I'm done with whatever we wanted to discuss. And it's already like 9:15, so I'm not sure how many of them are around.
Very quick.
Before
was left over, right?
What?
My bad. Yeah, just continue. Yeah, raise it later.
Vasu, before you continue, just one question for Manu sir. That's around the pattern again. Just want to make sure I understand.
Yes. Pattern. Okay, so it will be okay. The 60% of week 9 to 12, 20, and 20. Like 1 to 4 and 5 to 8. So that is 60-40 division. Like 1 to 8, you can consider of that. And what else?
So the questions will again be similarly broken like in quiz 2?
Yes.
A few of them not, because the question count is already going too far. I mean, so like whichever doesn't require, we don't have that as broken down. So, MSQSP we can't do that, and some numerical are there, which are like it makes sense when they are complete, like when they are together. Otherwise, doesn't make sense. For example, this question, when Does it make sense? Yeah, it is, but okay.
Sir, the
So the
paper,
objective behind that.
paper is
Where the
difficult.
No, paper will not be difficult. So I don't think so that you will come across any question which will be new for you.
so just one final thing is when I look at numericals from week 9 to 12. So
Mhm.
like in quiz 2, there were 2 weeks in which numericals were not expected. So is there something
6
like
and
that?
7.
So is that like that in week 9 to 12, or we can expect from everywhere?
You can expect from everywhere.
Okay, sir. Thank you. Thank you so much.
And so,
Yeah.
do we have any session on Friday for if we come across
Yeah,
any?
there were some doubts, but if you can, let's have a session on Friday or Saturday or Thursday, anytime
Not
for
Saturday,
doubt
maybe
clear.
Friday.
Okay. We'll have on Friday for doubts.
Yes, that would be very helpful actually to have one like
It's
proper
at
doubt
the
Yeah.
clearing.
So what you can do is before, let's say on Friday, at around noon or something, you can post all the doubts somewhere.
So
This
wait,
could be
Vasu's thread is there. Vasu's
yeah,
thread is
Vasu,
there. Can you pin
I
that?
think we covered LSTM GRU part, we covered decoder part also. One PMI question was there. So what we come across is use log given in the question. If not, then log base E is the standard we'll use for all the questions in this quick
Unless
quiz.
specified it is ln. I mean
Yeah,
exponential.
ln, yeah,
Okay,
exponential, natural
got it.
log. So we'll use natural log for everything. If it is there. So I think yeah. So we got 3, 4. If you have any further doubt, post in that. I saw that post, and so that's why I covered. I took more time in LSTM.
On that CBOW, we can, if you're too late today, we can take it up on Friday. But basically in skipgram, sorry, not CBOW, skipgram, if let's say the output is 4 words, then what is the W context parameter size? Is it into 4 times, or is it just
No, it is same. Whatever the size of W word, both have same dimension. Earlier, I also had that doubt, but even if you have multiple context to predict, still it is same only. It will not be
okay?
by
Okay,
double or by triple.
okay, got it.
So
Thank you.
that 2,500 answer is actually incorrect. It should have been 1,000 in
1000.
that question.
Correct.
Yes, correct. 1,000 only. Yeah, that also I wrote in
You,
the.
you you showed that, but the thing is, multiple instructors were showing different answers, and some people were saying the first logic is correct, some were saying the second logic is
Yeah,
correct. So yeah,
even I was confused because that's how when you see the PDF, it's like that. So what happens is in SIBO or in Skipgram, there are several variation of that is also exist. So sometimes from where you learned that also make a difference. But we'll go with our course. In our course it's like this. We take this weighted. You can call it as a weighted inputs. Like we sum them. Somewhere they concatenate it also. So that's not our case. Okay, we sum them. One vector, another vector, we sum them, so we'll have similar dimension vector. We'll not have double of that. Okay.
Sir, but the model should predict multiple outputs, right?
So that's okay, right? Let's say you want, let's say you want to predict 5 words. Okay. Um, yeah, 5 words. Okay. So what you will do is you'll have probabilities of all the words. You will choose top 5. That's how you do it.
So for each word, you'll have a probability distribution. But to
Correct.
calculate the probability distribution, you're using the same W context vector. That's what
Yes, correct. So same will use, but we'll use top 5. So how much context you want, right? 4, 5, 6. I mean, not odd number. Generally, we have even number. I mean, because they chose both the sides, so that's why. Uh, in paper, so I read the paper about it, and they chose equal window of both the sides. So that's why some even number would be that. And if you want to predict, let's say 6 things, then you'll have probability distribution of all the words. You will have top 6 words as a prediction.
Got it, sir.
So, sir, we already have a thread where we are adding questions for the end term. Vasu has started that thread, so we'll keep on adding to it.
whatever you can answer in the thread itself, we don't need to take up. Whatever are important things that you feel we should take up in the session, we will do that on Friday evening. So
Okay.
till we'll keep on adding to the thread no matter what. If you could
Yeah,
kindly
sure.
just keep on responding there. So most of the responses will take care of the doubts. So in the end, we will be left with like 5 or 6 questions which are critical, which need to be handled in person, which we can do in the session, if that is okay with you and everyone else.
Okay, sure.
Yeah, and I suggest you pin that thread as well, so that others can also just add there.
Yeah, okay. I'll pin that. I am looking.
That link is there in the chat. So Chaitanya put it in the chat just now.
Okay, okay.
And so
I'll
the
pin
session will be in the same time, 7 to 9.
7 to 9, like our regular session. We
Yeah.
had it.
Thank you, sir. It's very, very. Thanks for
Thank
agreeing.
you.
It will be very
Thank
helpful.
you, sir.
Also, sir, could you upload the practice and graded assignment solutions for week 12?
Week 12. Yeah, so
I-
for practice assignment, I'm not sure. So what I did is I shared. I think I shared
Video.
Video,
a video of that in the
video
in
link.
that. This graded assignment will be uploaded by tomorrow, for
Yeah,
sure.
because I had a question in graded assignment. We took the x vectors, x matrix to have column vectors, and then there we multiplied v with the the u transpose w, u q transpose k.
V with Q transpose.
What I mean is we pre-multiplied q transpose k with v, whereas in the lecture it was written q transpose k, the softmax of that into V transpose. So it
Yeah,
was,
Archit, with the question, it was given to take it V into Q transpose V.
yeah.
Yeah.
That's my question is like, when do we take what, like when do we pre-multiply and when do we post-multiply? Like,
So if the question is given to do it in a specific way, because I also made the same mistake till Vasu corrected me. So if it's made in the same, if the question is specified to do it in a certain way, you do it in that way. Otherwise, if it is not given, then we do Q transpose K and into V transpose. That's the correct.
Okay. There.
Sometimes what happens is the best way to do some of these things is, sometimes if it's unclear, you know what the output dimension should be, right? You know that it has to be a vector of whatever. There are 4 words and embedding is 3, let's say. So you know it should be 4 by 3. So then you adjust those multiplications to get to that. Sometimes that helps.
yeah, but like sometimes the problem is the matrices are square matrices. You don't know
Then
transpose them or not.
yeah, then we Bhagwan ke naam bas.
Because a similar question was in the practice assignment as well.
I know exactly what you mean. Practice, you did that Q transpose, whereas here they didn't, because they had given the dimensions and structures slightly differently. But in the GA, they very clearly mentioned that please take V into A, not A into V transpose.
Okay. Also in the practice one, X I believe had dimension 4 cross 4 and WQ had dimension 4 cross 2. So for finding the matrix Q, what do? We do WQ X transpose. Like how do we match the
So your output, your output is basically they're saying the embedding is in two dimensions, right?
like
So you have to do 4 cross 4 into 4 cross 2, so that you end up with a 4 cross 2.
so in that case we do X into WQ.
No, you are doing WQ into X.
So 4 cross 4 is X, right? So 4
Okay, okay, sorry, yeah, okay, sorry, correct. You are doing it that way, correct.
again, then now in this case we have X into WQ, but in the lecture it was WQ into X. So
That's what I'm saying. See, what does W do? W takes a certain input and converts it into a certain embedding, right? So whatever that W is, that D cross V, sorry, N, it's N cross D. So N is the input, D is the dimension of the embedding. So I just use that logic and put it together, and usually it works out.
okay.
I'll try and sorry, your handle is what on? I'll try and put up my answer. Maybe it'll help. What is your Archit, right? Archit. Okay, I'll see if I can put up my working.
All right.
Maybe it will help.
Yeah, thanks.
Okay, great. In that case,
Yeah,
we
thank you,
can
sir.
close today's
Thank you,
session.
sir.
Yeah,
Yeah,
thanks.
Sir,
good night.
one quick question, if you can, just wanted to clarify something. There are these questions that ask for calculation of parameters and stuff. I wanted to clarify, in general, if nothing is mentioned, do we consider bias or do we not consider bias? I keep making the same mistake multiple times. I just wanted to get clarity on this.
Manoj, any suggestions?
No bias.
Don't consider bias. Yeah, no bias.
If nothing is mentioned.
Yes, if nothing I mentioned, no bias.
Okay, but I just wanted to
Why is that?
just.
So, I tell you why is that, because when we so Mitesh sir confirmed it. He said so if there is a question with bias, he said remove the bias, because that's how he always taught this. But sometimes this thing, right? I think GRU and LSTM specifically, they where B and in RNN also, where they have specifically used it. Otherwise, they never use bias. Mostly he skipped it. So that's why.
Okay.
Don't
So
consider.
my question was not specific for GRU or LSTM, by the way. I was asking in J. So let's say for even for an FF feed forward network parameter calculation, if nothing is mentioned, do we not consider bias?
Yeah. Don't consider bias.
Okay. Just wanted to put it for the record that this goes against whatever has been done for PYQs. The previous terms, I kept not using bias and I kept getting those answers wrong. So okay, we are changing the trend now. I understand.
So,
Yeah, but now the instructor is clearly stating, right? So no bias means
Yeah.
let's go with no
in
bias.
the feed forward I remember in quiz 2 also, in one of the questions, it clearly said that, in the course we haven't considered bias. So even here we are
Correct.
not biased. So I think in LSTM and GRU, when they give the equation, if there is a B or C mentioned, then we have to consider bias. I think that's what Manoj
Yes.
is trying to say.
If BNC is
Yeah,
given, then
that's
you
all.
have to consider bias.
Understood. Thanks.
Okay.
Thank
Okay.
you
Bye.
so much, sir.
Thanks everyone.
Thank you.
Thanks, sir. Thanks, Krishna.
Thank you,
Thanks.
sir. Thank you.
Thank you,
Good
sir.
night.
Very nice session. Thank you.
Thank you, sir.
Thank you, sir.